Okay, this looks like it's working now. Okay, great. Okay, so someone's audios. All right. So anyway, on CCLE, there's a page. I sent out an announcement also. Thank you to our two teams who have put their names up. Okay, and you'll need to set up a GitHub for the repository. That's where you're gonna basically submit your work, and you can have up to 4 team members. Okay, you need to have a minimum of 2, and if so, I kind of made an example where I said I'm Miles and I'm working with Red Shirt Smiles, and if you want additional team members, you can kind of list it as well on the team page, and then maybe somebody will be willing to join. We'll also spend some time on Monday after our quiz to have people try to find teammates or something. But I would like it if you guys spend some time this weekend to just say, hey, do you want to be on my team? Sure, great, and then fill it out. Okay. And we'll go from there. Okay. All right. Any questions about that? Getting your teams up and running? Okay. Another thing, and I should have realized this, but so everything that I've been doing has been I've been posting my notebooks to this repository on GitHub. Okay, and it's set up so that if you clone it, you can just pull the updates very quickly. Okay. The problem is that if you modify the files on your local machine and you commit them, then your repository will fall out of sync with the one online, because you're not allowed to push changes back to my repository. But that might be something you guys want to do. Okay, so cloning and then just pulling updates works if you are not making any changes. But if you want to make changes and commit them yourselves to your own local repository, and still receive updates from mine, then what you actually need to do is you need to fork. You need to fork the repository. Okay, and so what a fork does is it creates a copy of it on your own GitHub. Okay, so when you clone it, it just clones it to your local machine and it doesn't exist on your GitHub. Okay, but when you fork it, it creates a copy. Maybe I'll illustrate this. This is a different class. I'm teaching too many classes this quarter. Forking on Git. Okay. All right. Okay. So this is my Miles's repository. Okay. And basically, I can make commits and so on, and there's another commit, and so this happens. But you can create a fork, okay? And what the fork will do is, it looks like I'm writing something else, huh? I'm trying to write fork. F-O. Why is this so hard? Okay.
You can throw a fork.
All right, there we go. There we go. That's what I want to write. Okay, so when you fork the repository, this establishes on your GitHub. Okay, so this is a new repository on your GitHub. Okay, in your account. Okay, And then what you will do is you will clone to your machine. Okay? And basically, now you have a copy of this repository, okay? And then you can make changes and update. So then you can kind of, make changes and then push them back to your repository, okay? So you can clone to your machine, and then you can make changes and push back to GitHub. Okay. But when you fork it, when you clone it to your machine, you are able to set two upstreams. Okay. You can have so normally you set a remote, and when you clone it, the remote it defaults to being the thing that you've created, right? So when you fork it, so on GitHub, we start off with my repository. You fork it, which creates a copy on your repository, and then you clone your forked repository onto your computer. Okay, you can, and so now it's like you just have a remote and your local, and then you can keep pushing things back and forth. But on your local repository, you can set a second upstream, a second remote. Okay, and you can link it back to my original repository. Okay, and so what you can do is on your local repository, after I make changes, you can fetch the changes that I've made on my repository, and that will update your local machine, and then you can push those changes back to your forked repository on GitHub. Okay, and that way you can make changes on your local machine and make changes to the notes and stuff, and still get updates from my repository, if that makes sense. Okay, so clone machine, make changes and push, but also set a second upstream to get updates from my repository. And so this is detailed on these two pages. Okay, fork a repository and syncing a fork. Okay, so here's the fork that you want to do. Okay, so you're going to find my repository, and then on my page, you're going to click fork. Okay, I can't fork my own because I'm the owner. Okay, but when you're logged into GitHub, you click fork, and it creates a copy on your GitHub. Okay, and then what you'll do is you create a local clone of your fork, right? So once you're in your forked things, you're going to click clone, right? You're going to clone it into your local machine using git clone, okay? And it does that, right? And then you have to add a second remote, okay? So it says configure git to sync your fork with the original being my repository, right? And so what you'll do is you're going to use this command, git remote add upstream, okay? Because if you do remote -v to view your current things, it's going to be, it'll have origin, and it will be your name and your fork. But what you want to do is you want to add an upstream, okay? So you're going to do git remote add upstream, and then you're going to paste in the URL of my repository. Okay, so git remote add upstream, and then you put in my repository, and then when you view your remotes, there will be a listing of 4. Okay, there's going to be your thing, which normally goes with git push. You'll push your changes to your repository, but then you can update the files whenever I make a change when you fetch from Upstream. Okay, I don't know if that makes sense. So it's basically you're creating a separate repository that you can synchronize with GitHub, and you're pulling changes whenever I make a change to my thing, okay? And then to synchronize it, you'll follow these instructions, and basically you're going to do git fetch upstream, and then you're going to merge what you just fetched. Okay, so you're going to do git fetch upstream and then git merge upstream master. So kind of the steps here are create fork on GitHub. All right, it's better if I just type. Look at this. All right, so one, let's create a fork on GitHub, okay? Clone your repository from GitHub to your local machine. 3, add a second remote to your local machine's repository. Okay, and this will look something like git remote add upstream, and then it'll be a URL of my GitHub repository. Okay, and now you can push local commits to your forked version on your GitHub. Okay, but then you can pull changes on my repository to your local repository, and that's going to be done by doing git fetch upstream. Okay, and then you're going to have to do git merge upstream master. Okay, so this will merge changes that I've made to your repository. Okay, and then you can push these changes back to your forked version on your GitHub. Okay. All right, so anyway, otherwise, you know, the git clone and the git pull works if you're not making any changes to the files, but during office hours, it took a little while to figure out what was going on with the students' issues, but we figured it out, and so I wanted to share with you guys. Okay, let's take a look at stuff today. Set up Jupyter Notebook. Okay, just wanted to wrap up. We'll go back to a Numpy a little bit, wrap up a few things there. It's kind of just a little bit of a mix of topics today. We didn't get to finish Lambda functions, so I just wanted to run a few examples of Lambda functions, and then do a little bit of linear algebra in Numpy, show off some of Numpy's linear algebra features, and then if we have time, I want to just kind of introduce the very basics of pandas, okay? Because pandas will serve as our primary vehicle for handling data in Python. Okay. Okay. So anyway, Lambda functions basically allow you to create your own function in line without the need to formally define a new function. Okay. So we were always able. So just as a setup, we were always able to define new functions, okay? You just say define the name of the function and then what that function is going to do, okay? But if that function is going to be very simple, you might not want to like define the function separately, okay? Especially if it's a simple function that's going to be used only once, okay? Because then you've got to define it and then you've got to call it. And then, you know, as far as a readability thing goes, if it's only going to be used once, and somebody's reading through the thing and they see the name of a function that they don't recognize, you know, they might have to search back a few lines to figure out exactly what that function is doing. Okay, so you know, if you're going to use something just once, it makes sense to define it right there. Okay. And then so here we can define this function called replace space, okay? And then map is like apply. In R, you have the apply function, which takes a function and applies it to all the elements in a list or vector. Here you have map, which does the same thing. And so here, replace space basically searches using regular expressions. It searches for two spaces and replaces it with one space, okay? And if I run that on a map, and then if I want to actually, when you do a map, it returns a map object, and if you want to actually see the contents, you gotta pipe it into a list or put it into a list or something. Okay, and so we can see that it has successfully replaced the two spaces between South and Carolina into a single space, and then there were three spaces in front of Alabama. And so there's now only two spaces there, okay? So it just replaced two spaces with one space. So that works just fine, okay? But because this is such a short little thing, this command right here, where I'm running the function map, and I give it the name of a function, okay? I can just say lambda x, okay? And this means I'm declaring a new function without formally defining it, okay? And so what this says is take, and it basically just says, you know, return this expression, okay? So what you're going to do is you're going to do re.sub, okay, regular expression, substitute two spaces with a single space on the string x, okay? So this is a function of x where it's going to do the regular expression substitution on x. And so if we do that, we're going to get the exact same result. Okay. So here's another function, another lambda function, where it's going to take in an argument x. And I think lambda functions are often written with x, but there's nothing that stops you, and you can just call it, you know, lambda string. So you can kind of, it's a lambda being applied to a string, and what you're going to do is you're going to take the string and apply title case to it, okay? So if we do that and apply it to states, we'll notice that, you know, the funny capitalization in Florida goes away, and we have this, okay? But string.title did not do any space substitutions. So this is because we just applied it to states here. Okay. So so here I've combined several things, and you know, maybe this is now at the expense of readability, but you know, a slightly more complex example, all right? And so for each element in states, okay, we're going to map this function to it. And so it's going to be a function of x, okay? And it's going to substitute this punctuation, question marks, pound signs, and exclamation points. It's going to just replace them with nothing, okay? But it's not applying it to x directly. It's going to apply it to x after we've applied title case and stripped extra white space. Okay, so it's not being applied to x directly, but x after we've applied title case and stripped the extra space. And so this comes out just a lot cleaner here, okay? So lambda functions, they're just generally written in the form of lambda argument, colon, and then the expression to return. So in all of these cases, it's just been like lambda x colon, and then the thing that you want it to return. But you are allowed to have multiple arguments, okay? So here I've got a lambda function of x and y. So lambda function of x and y, and all it's going to return is x plus y, right? So that's the function we're going to apply. And so on map, we need to give it basically lists for each argument. So I'm going to provide it for x, 1, 2, 3, and for y, 100, 200, 300. Okay, and so when we map this lambda function to these values, we get 101, 202, and 303. All right. Okay, and again, all of these things, all lambda does is it just saves us a little bit of typing. So instead of having to formally define and name a new function, we can just create a new function in line with whatever command that we're using. So if we're using a different function that allows you functions as arguments, you can just write out the lambda function right there. Okay. All right. I want to show a few linear algebra examples with Numpy here. Okay. So here you could create an array. It's just 1, 2, 3, 4 for x. You can create the same thing with y, doing this. A range 1 through 5, reshape 2, 2. So whichever way feels more natural for you, you can do. Okay. And then so the asterisk does element-wise multiplication. So it's going to do 1 times 1, 2 times 2, 3 times 3, and 4 times 4, and we get 1, 4, 9, 16. Okay. If you want matrix multiplication, which you had to learn in linear algebra, where it's like this element multiplied by this element plus this element multiplied by this. So it's going to be 1 times 1 plus 2 times 3. Wait, 1 times 1 times, plus 2 times 3. And we get 7 in the top left corner. And then the next corner will be 1 times 2 and 2 times 4. So to give us 10. Okay? So on and so forth, you can use the @ sign. So the @ sign would be equivalent to, in R you have %*%. The @ sign in Python is the infix operator for matrix multiplication. Okay. You can also there's np.dot. Okay, np.dot does the same thing. Okay, so x at x is the same thing as basically the dot product between an x and x. Okay, and then you can multiply something by its transpose, and you'd get this. Okay. I don't know. Do you guys remember, like, so in simple linear regression, let's say you want to model y hat as b0 plus b1x. Okay. In linear algebra, did you guys learn this? That your estimates of beta will be x transpose x inverse x transpose y. Okay. And so you have to, if you have a intercept and x variable, the the X matrix needs to have a column for ones for the intercept, and then the X values, right? So in our case, I'm going to produce an array. I'm just going to have the values 1, 1, 1, 1, 1, and 1, 2, 3, 4 for X, and then Y will be 2, 6, 4, 8, okay? So when I do this, basically X is 1, 2, 3, 4, and Y is 2, 6, 4, 8. We haven't covered Matplotlib, that'll come later, but just to kind of show what this looks like, you know, it looks like this, and we want to fit a linear function to this. So again, doing b hat x transpose x inverse x transpose y. This can be done using linear algebra. So I have x transpose times x, and I want to invert that. So I use the function numpy.linearalgebra.inverse. Okay, so that'll be the inverse of whatever matrix you put in here. So that's going to be x transpose times x. And then we're going to multiply that by x transpose times y. All right, and so when I run this, I get 1 for my estimate of the intercept and 1.6 for my estimate of the slope. Okay, and so like just in case you aren't convinced, I don't know if R would convince you, but probably, you know, so to do this in R, you would just do 1 through 4, and Y would be 2, 6, 4, and 8, right? And then you do linear model Y explained by X, and so this will be our model. Okay, and then I would, summary model? Oh, that's too much. Okay, so if I just call model, it'll say the intercept is 1, and the coefficient for X is 1.6. I mean, I guess that's fine right here when you have summary. The estimate is 1. You know what? It's just because. All right, this looks much more reasonable. Okay, so we have 1 and 1.6, and that's exactly what we have. And we could have done this in R also using the linear algebra. That's what I have to do. I have to do solve of transpose. Oh no. So I have to update X as cbind repeat 1 4 times and X. Right, so X is this. Okay, and then Y is going to be matrix of Y. Okay, so then I would do solve X transpose X times X transpose times Y. Okay, and we get the same thing, 1.0 and 1.6. All right, anyway, so that works, okay? You got we have a bunch of these linear algebra functions. I mean, you can always go to Numpy linear algebra. I just want to kind of demo some of them, right? So here, if I do X transpose X, we'll get this, 4, 10, 10, 30, okay? And so we saw this, the inverse of X transpose X will be 4, 10, 10, 30, and then here, let me just kind of, oops. So if I do X transpose X times its inverse, what should I get here? Okay, I get the identity, right? Which is exactly what I want. 101. Okay. We can do Cholesky decomposition. So the Cholesky decomposition produces a lower triangular matrix that, when multiplied by its transpose, produces the original. Okay, so here I have, so X transpose X is 4, 10, 10, 30. Its Cholesky decomposition is 205, 2.23, and A times A transpose. Okay, so if I say A times A transpose, I get back the original 4, 10, 10, 30. I don't know, you guys remember this stuff from linear algebra? QR decompositions, okay? So QR decompositions will produce two matrices. One is Q, the orthogonal one, okay, which looks kind of crazy like this, and R will be upper triangular, okay? So notice because a QR decomposition is expected to return two matrices, a Q and an R, I can just use tuple unpacking and assign Q appropriately, okay? So Q times R is the original matrix, and Q being orthogonal, Q times its transpose will give the identity matrix, okay? And well, it's almost exactly the identity. I have 1 in the diagonals and then something very close to 0 in the off diagonals, okay? It's because of floating point imprecision, we get this, but that's what we have. Okay, and then you have you can find eigenvectors of a thing. Okay, what are the eigenvectors of a matrix? So if you have a square matrix and you find its eigenvectors, what's special about that? Okay, so basically when you multiply we should make you watch videos on linear algebra, but when you multiply a vector by a matrix, a lot of times it applies some kind of transformation to it, okay? And if it's a square matrix, then it keeps it in the same dimension space, but the multiplication can either like provide a rotation or a skewing or a shearing thing, okay? But there are some vectors that when you multiply them by the matrix, they end up pointing in the exact same direction that they were pointing before, okay? And so it's no different than multiplying by a scalar. This is generally not the case. When you multiply a vector by a matrix, it's generally going to change, but the eigenvectors are special vectors associated with the matrix that says when you multiply the eigenvector by the matrix, it's the same as multiplying by a scalar. Okay, so anyway, you can use numpy.linearalgebra.eig to find the eigenvectors and eigenvalues. Maybe I should write eigenvalues and eigenvectors, because that's the order that they come in, okay? So you'll get the values and the vectors, okay? You print out the values. We have two values, 0.6 and 33, okay? And the vectors are in the columns of the vector. So here I'll take the first column of the vector output here, and we say if we take the matrix and we multiply it by its vector, I'm going to get another vector, okay, which is expected. But it turns out that this other vector is exactly the same as if I take the eigenvector and just multiply it by a constant. Okay, so over here we have a matrix being multiplied by a vector, and over here I have the vector being multiplied by a constant, and they end up equaling the same thing. All right, and so that's generally not the case, because when you multiply a matrix by a vector, most often it'll do some kind of, it'll end up pointing in a different direction. Okay, and then and you have two of these, so you could do the same thing with the other set of eigenvectors. Okay. Oh man. Okay, we got like 10 minutes left, which is not enough to even do anything interesting with pandas, but too much to just, I don't know. Should we just call it a day, or should we start pandas? Just call it a day. Okay. Well, it is Friday. So, all right. Okay, so we'll call it a day. We'll start our pandas on Monday. Okay. Pandas are really exciting, and we're going to spend a lot of time in pandas because there's a lot we can do. So okay, see you guys on Monday.